Hey guys, we're here with this sweet pressure washer that we dug up out of my garage. We're a little bit low on money right now, so we're thinking about selling this bad boy on Craigslist.
We tried to sell it, but it wouldn't sell because we don't know any of the specs on it. And people really like specs, so we're gonna have to calculate it.
We would have had the specs, but some vandal has covered all the labeling up with these dirty stickers. So we're gonna have to figure it out ourselves using this here 5-gallon bucket. We're about to attempt to start this for the first time in many years. Here we go.
Alright guys, so what we got here is a 5-gallon bucket. We're timing how long it takes to fill it up so we can calculate the volumetric flow rate. That's time. 5 gallons in 2 minutes and 57 seconds.
Alright, ladies and gentlemen, welcome to the Fluids Lab. We're here to do all the calculations. You saw us conducting the experiment with the bucket and the pressure washer to try and get the numbers and figures for us to do all these crazy calculations. People are interested in more than just flow rate with these pressure washers, so we're also going to calculate the pressure in the tube going to the nozzle before it comes out.
Yeah, and actually I was doing some research on Craigslist, and one thing I noticed is people honestly don't really care about the nozzle. It's kind of weird, but people are only concerned about the tube before the nozzle. I think it has to do with the fact that it's a little harder to change than just swapping out the tip of a nozzle.
I thought we were doing the drone scene later.
No, okay, hey, let's not do the drone scene yet, okay? Not a sponsor. Well,
No drone.
Alright guys, so this is our flow rate calculation. We used a 5-gallon bucket to fill up with the pressure washer, and it took 2 minutes and 57 seconds, which converts over into 2.95 minutes. All we did to get our volumetric flow was divide the 5 gallons by the 2.95 minutes to get there, and that gave us 1.69 gallons per minute. We had to convert that over into foot cube per minute for calculation's sake, and we ended up getting 0.226 foot cubes per minute as a volumetric flow. Next is surface area calculations. We measured the diameter of the nozzle and the diameter of the tube leading to the nozzle. We plugged into the surface area formula, which is diameter squared times pi divided by 4. That gave us a value for the nozzle of 9.85 times 10 to the negative 6 foot squared, and of the tube, 0.001169 foot squared. We use surface area in this equation to find velocity, which is velocity equals flow rate, volumetric flow divided by surface area. We just plugged straight in. We had those values calculated, but we converted right here to feet per second from feet per minute. That gave us 382 feet per second coming out the nozzle and 3.22 feet per second going into the nozzle. Okay, guys, so now we're going to use Bernoulli's principle to calculate the pressure going into the nozzle. So we have it laid out here, but we canceled out the heights because it's such a small diameter and such a small tube that they're essentially the same. The pressure too here we're canceling out because we're using gauge pressure, and at atmospheric it would be 0. We use the gravitational constant of 32.2 feet per second squared with a gamma of 62.4 because we're using English units. This is just getting Bernoulli's in the form that we need to solve for pressure. And here we're just plugging all of our values that we've calculated and defined. And we get our answer in pounds per square foot. We divide that by 144 pounds per square inch as a conversion factor. You have to, there's 12 inches in a foot, and you have to square it, so that's how we got 144. And that gives us 983 psi G going into the nozzle.
After going through the entire experiment and testing everything we needed to test, we had a pressure right before the nozzle of 983 psi-G. We also had a throughput of 1.69 gallons per minute. Yeah.